Hi everyone. Welcome to Earth 120 lecture on April Fool's Day. You might notice that I am not Dr. Gleason. I am Alex, the GSI for the Thursday and Friday lab sections, and I'm going to be giving your lecture today for Earth 120. Just a brief announcement before we get started on the lecture. The quiz for lectures 17 and 18, the quiz is due at 6 p.m. today on April 1st, so 6 p.m. April 1st. And information regarding your next quiz for these lectures will be posted by Dr. Gleason later. So I'm going to be giving the lecture today, and on Monday, Dr. Gleason talked about snowball Earth and Precambrian climate. So now I'm going to take the baton from him and blow through Phanerozoic climate, so an evolution of Earth's climate history during the Phanerozoic, but with a twist, with relevance to current anthropogenic global warming. So I'm not going to be talking about every period and epoch in the Phanerozoic. That would take way too long. So we're going to talk about a couple points of interest in the Phanerozoic with reference to today. So this is a temperature curve through the Phanerozoic. So you'll see that this is globally average temperature. And I want to walk us through this graph because I'm going to come back to it several times in this lecture. So you'll see over here on the right side, this is where we are today, and it shows where we might be in the near future in terms of temperature. So in this part, we are in the Holocene, and we're talking about thousands of years before present. Once we get to this little block, we start to go to about 200,000 year intervals, and this is in the Pleistocene. You can see the Ice Age cycles. Then we get over here to millions of years, and we are in the Pliocene, going back to now tens of millions to hundreds of million years, all the way back to the end of the Phanerozoic there. So I'm going to talk about several periods within the Phanerozoic several times, and the first is the Carboniferous and the Permian, which were about 359 to 252 million years ago. Then I'm going to skip ahead to the Paleocene-Eocene thermal maximum. This was between 56 and 55 million years ago. Then I'm going to skip way ahead to the Pliocene epoch, which was 5.33 to 2.58 million years ago. And then after that, the Quaternary, which is 2.58 million years ago to the present. And you've already learned about the Pleistocene and the Holocene epochs, so these are contained within the Quaternary. And we currently live in the present at the end of the current end of the Quaternary. Then just briefly at the end of the lecture, I'm going to talk about the present and future anthropogenic climate change with reference to our national parks. So when we're talking about climate change on Earth, we are really talking about carbon dioxide as the first order control on Earth's climate. So carbon dioxide, or CO2, is basically the dominant control on Earth's climate. There are other other mechanisms that can change Earth's climate, but they either happen on a short time frame or they do not happen to the same degree. They do not control Earth's climate to the same degree as carbon dioxide does. So here you can see the fluctuations in Earth's temperature and fluctuations in CO2 over the last 800,000 years. And you'll see that they really follow the same pattern. So this is showing us that there really is this first order control of carbon dioxide on Earth's climate. So carbon dioxide is a greenhouse gas, and it warms the Earth by the greenhouse effect. So what a greenhouse gas is something like CO2 that can absorb infrared radiation. Now, why does this actually warm the Earth? Well, as this graphic is showing you, sunlight comes to the Earth called incoming solar radiation, and then as the Earth intercepts that sunlight, some of it is reflected, but other sunlight is absorbed and then re-emitted as the planet's outgoing radiation, which we call infrared. And that infrared radiation is then absorbed by gases like greenhouse gases and re-emitted back down to the Earth, basically warming our atmosphere. So greenhouse gases like CO2 essentially act as a blanket around the Earth. And we like the greenhouse effect because without it, we would not be here today. The greenhouse effect keeps us warm and allows us to live on Earth. But if we added more carbon dioxide, the greenhouse effect would warm the Earth further, which is what we're seeing today with our current anthropogenic climate change or global warming. So now that we know about carbon dioxide as the first order control on Earth's climate, we're going to look back to the Carboniferous and the Permian, which is all the way back here. And you'll see that it's actually a time of lower temperature, more similar to what we have today, even a little bit lower. That's because the Carboniferous and the Permian were another time with ice sheets on the Earth. This is a plot of Phanerozoic carbon dioxide. You can see that carbon dioxide during the Carboniferous and the Permian was on the lower side, still higher than today, but much lower than before and during the Mesozoic. So this was a time with glaciation on the Earth, but like today, it had warm and humid tropics. So this is very important because these warm and humid tropics allowed for shallow seas and swamp environments in the southwestern US, shown here by this red circle. And this is where many of our fossil fuel deposits were formed. So you might have heard of an area called the Permian Basin in Texas. This is one of the most prolific fossil fuel developing areas of the country. And that's because of these fossil fuel deposits that were formed from shallow seas and swamp environments and the tropical plants within them that were then buried and turned into coal, oil, and gas. We have evidence of this Carboniferous and Permian shallow sea and swamp environment from Guadalupe Mountains National Park. This is a great national park in West Texas. I have not been there myself yet, but I would love to go anytime now. And this has the highest point in Texas called El Capitan, which is a giant limestone monolith. And it was formed by the shallow sea environment in an ancient coral reef from the Carboniferous and Permian. So this is evidence just on the west side of the Permian Basin of these shallow sea environments. We also have evidence from the Carboniferous and the Permian of all these marine transgressions and regressions in the Supai group of the Grand Canyon. So during all this time of changing sea level, we have sandstone, siltstone, and mudstone in the Supai group that contains all this evidence, but further to the west, so there are no oil deposits in this group. What I want you to know about the Carboniferous and Permian and why it's so important to our present day climate is it actually holds evidence for the human fingerprint of global warming. So where does this evidence come from? It actually comes from the tropical plants that formed our fossil fuels, and specifically from the isotopes of carbon from the plants themselves. So you may have learned about isotopes from general chemistry, you may not have. That's okay. I'm going to give you a crash course in isotope geochemistry, and if you want to learn more and get more into the details of isotope geochemistry, there are several classes in the Earth department that teach this. So here we have a carbon atom, and this is the normal carbon-12 atom, which means that it has an atomic weight of 12, 6 protons, and 6 neutrons. So this is what most of the carbon atoms are, about 99% of them. This is the normal one, and it is included in what we call the stable carbon isotopes. So the stable carbon isotopes are carbon-13 and carbon-12. Carbon-14 is a radiogenic isotope, which means that it decays over time. We've talked about that with carbon dating. We do not include that here in our stable carbon isotopes. So carbon-13 and carbon-12 have significance. So carbon-12 has the 6 protons and 6 neutrons, but carbon-13 has an extra neutron. So it is heavier than carbon-12, and that is really important, especially for plants, because it is not as efficient for plants to use during photosynthesis. So this is really important because that means that plants have a much lower ratio of 13 carbon to 12 carbon. And we can measure that as the isotopes through time. So if plants have this relatively low ratio, this means that if the primary reason for our current global warming is fossil fuel combustion by humans, the ratio of 13C to 12C, which we can also call in a little bit different form delta 13C. It's the ratio plus a little bit more math. This should be decreasing over time as we're burning fossil fuels, or we can also say it's going more negative because negative values of delta 13C, this guy here, negative values means that there's a much lower ratio of 13C to 12C. Positive values mean there's a higher ratio. So let's see, is this holding true? Yes, it is. So this is a plot of showing delta 13C of atmospheric CO2. You'll notice that it's getting more negative as we go up, so the axes are kind of reversed. But this is showing that as we've burned fossil fuels since about 1800 and going towards today, that the signature of delta 13C is becoming more negative. And this is consistent with our idea that plants and tropical plants from the Carboniferous and Permian have this more negative signature, so as we're burning them, we're releasing those negative isotopes into the atmosphere, and it's causing the atmospheric delta 13C to go more negative. So this is very, very important because the Carboniferous and Permian are really holding one of the best lines of evidence to show that our current warming is anthropogenic in nature, so humans are causing it, and it is not from some other natural cause like solar irradiance or volcanism. So overall, what I want you to know about the Carboniferous and the Permian is that it's when our fossil fuels were formed, and it holds the evidence that current warming is caused by humans through that delta 13C concentration of the atmosphere. Okay, so that's the Carboniferous and Permian. Now we're going to shift gears and move forward to the Paleocene Eocene thermal maximum. This is also called the PETM. It's a very popular time to reference in paleoclimate. It was about 55.5 million years ago, give or take. It was a fairly short time in Earth's climate history. It's this green blip that shoots up and then comes back down in temperature. So what is the PETM? This was a time of rapid climate warming. So here you'll see the paleogeography of the Earth at this time. During this time, there was about 5 to 8 degrees of Celsius warming over 20,000 years. So this is actually a very short amount of time to have such intense warming. And because of that, it is the best analog for our current rapid global warming. We can see that the current global warming rate, however, is even faster than the PETM, which so far in Earth's history that we can tell was before the most abrupt warming, and now we are surpassing it. So this graph is showing you the rate of our warming, and it's taking only a couple hundred years, so about 22 to 2300, to reach the values of the PETM, which took 20,000 years. So even though it is the best analog for our current rapid global warming, we are warming at an even quicker rate than the PETM. So CO2 during the PETM in the atmosphere was between 1,000 and 2,000 ppm. ppm stands for parts per million and is the way that we measure carbon dioxide in the atmosphere. So how many parts per million parts is CO2 versus everything else in the atmosphere. So 1000 to 2000 is a much different world than today, because today we are at about 400 ppm, but we're growing. And we've actually started at about 280 ppm in the Industrial Revolution when we started burning fossil fuels, and we've raised to just over 400 today. So just to reinforce this point, in the PETM, there was about 0.24 gigatons of carbon released per year into the atmosphere, which was a large number for the Earth, but today we're releasing much more, and that's leading to our faster rate of global warming, which is about 10 gigatons of carbon per year. So if we think we're on a similar course and heading towards something like the PETM with our global warming over hundreds or thousands of years, we have to know what the Earth actually was like during the PETM. So it was much different than the Earth is today. There were no polar ice caps, and instead there were things that we kind of associate with tropical environments like crocodiles. There's evidence of crocodiles up in northern Canada and fossils of plants like ferns. So this was a much different environment, much warmer temperatures up at the poles. The tropical rainforests existed much farther north and south towards the poles than they do today. Today they're kind of capped between the tropics, so between 30 north and 30 south degrees latitude, but they expanded much farther towards the poles. The ocean temperatures were much, much warmer. They reached, we think, up to 68 degrees Fahrenheit off the coast of Antarctica. So the PETM was a climate that is so different than what we have today. And this photo was used actually by an activist. And it's exaggerated a little bit depending on where you think you are in this photo. I think this is either in northern Canada or Greenland. But it is trying to show that a tropical-like environment that we think of as tropical in the PETM was in this region. So if we have crocodiles and fern plants, something that would have looked like this swampy tropical environment did take place closer to the poles. So how could this time in Earth's history have warmed so quickly without something like humans to burn a lot of fossil fuels? The leading hypothesis is that large-scale volcanism may have caused this rapid warming. Due to movement of plate tectonics, there may have been large-scale volcanism in the North Sea near Europe, and this may have caused massive outgassing of CO2, which now we know that CO2 is a dominant first-order control on Earth's climate. So all of this quick, and by quick I mean geologically speaking, this quick outgassing of CO2 may have caused this rapid warming. Now, some evidence of Eocene volcanism, this is a couple million years after the PETM, so it's not the same large-scale volcanism that caused the rapid warming, but just a couple million years later, in the Eocene, we see fossil forests in Yellowstone National Park on Specimen Ridge. So this is an area that if you go to Camp Davis, I get my one plug of Camp Davis for the lecture. If you go to Camp Davis, you'll probably go and hike along Specimen Ridge. I show this Specimen Ridge day hike link here if you want to learn more about it. This is my favorite area of Yellowstone. You get to see these petrified forests of fossil trees that are thought to have been created by volcanic debris flow that preserved these tree trunks, much like what you learned about in Petrified Forest National Park in Arizona. And this is just a beautiful view of the Lamar Valley. You can see bison and sometimes grizzly bears and wolves along the hills. So this is my favorite part of Yellowstone, but it holds an example of these Eocene fossils. So changing gears for the PETM, we want to know actually how we know that it was so warm during that time. We don't have thermometers back then. We have to use evidence that is indirect about temperature. This evidence comes in the form of what we call proxies, and I want you to know this definition and what a proxy is. So proxies are sources of climate information from natural archives that can be used to estimate the climate conditions when measurements cannot be taken. So we only have measurements back to sometime during the 1800s, but any time before that we need a proxy to understand what the climate was like. So during the PETM, we have a proxy called foraminifera. So you may have heard of foraminifera before. Sometimes they're referred to as forams. These are single-celled marine plankton. And what makes them so interesting and important is they make calcium carbonate shells, like you can see here on this picture, and they're very, very tiny. They float all throughout the world's oceans. And in their shells, they actually preserve oxygen isotopes. So this time we're talking about oxygen, not carbon. And for oxygen isotopes, we're looking at 18 and 16O. So in their shells that get preserved in sediment cores around the world, these foraminifera can tell us the temperature of the ocean water in which they live in based on the ratio of their oxygen isotopes. So if you want to learn more about how this works, you can take other paleoclimate courses in the Earth Department. But basically for this class, I just want you to know that the oxygen isotopes preserve information about the temperature of the ocean water. So that is one way that we can tell the temperature of the PETM. So when we look at the foraminifera delta 18O and delta 13C, here on the left, you can see this rapid decrease in the delta values. So here in 18O and here in 13C, this is showing that rapid warming in the shells of these foraminifera. And then zooming out to a longer time, you can see this spike basically here is the PETM at about 56 to 55 million years ago at the boundary between the Paleocene and Eocene. So that is what you're seeing in this foraminifera, and we can convert these delta 18O and delta 13C to the temperature and see how much the temperature swung, and we know that it increased about 5 to 8 degrees Celsius over this time. So overall, that's the PETM. What I want you to remember about this is that it's the best analog for today's abrupt global warming. Okay, and we can infer these things from the proxies of foraminifera. So now we're going to shift millions of years towards the future. So we were in the PETM here, and now we're moving all the way to the Pliocene, which is about 5.33 million years ago to 2.58 million years ago. So you'll see that global temperature has gone down steadily since the Eocene into the Pliocene. So what's important about the Pliocene? Well, it was actually the last time that carbon dioxide was as high as it is today. So this figure shows a very similar plot to what we saw before, but now it's in carbon dioxide, parts per million, or ppm. And if this is where we are today, you can look back, and about 5 to 2.5 million years ago, this is when carbon dioxide was 400 parts per million, which it is today. So one way that we know what carbon dioxide was then is the same proxy that we use for the PETM. This is foraminifera delta 18O that tells us that Pliocene CO2 was 400 parts per million. So the same proxy that tells us the PETM tells us the CO2 of the Pliocene epoch. So if the Pliocene is like today's climate, if we stopped burning fossil fuels today and just let this 400 parts per million kind of run its course, it would warm the Earth to about what the Pliocene was. So these are global temperatures about 2 to 3 Celsius higher than today, and global sea level was actually 25 meters higher. So if that's going to happen today is highly uncertain, and it would take several hundred thousand of years maybe, or maybe not. We're still trying to figure that out. But what we do know about the Pliocene is that there was little to no ice on Greenland, even though there was ice on the Antarctic ice sheet. So all of this ice that melted from Greenland went into this 25 meters higher sea level. There also were warmer temperatures that allowed a different distribution of animals and plants. So this photo here is really showing different artistic renditions of the types of animals and plants that may have lived during this time. And evidence of some of these is actually captured in one of our national parks in the US called the Hagerman Fossil Beds National Monument in Idaho. You may not have heard of this before. I certainly had to look it up. But now that I know about it, it sounds pretty cool and I want to go visit. It has evidence of the Hagerman horse, which for paleontologists is a really cool organism and cool fossils to have, because it apparently only walked on a single toe on each leg. I don't know a whole lot about it, but it sounds like a really cool fossil. But it shows the different environment, what I care about as a climatologist, the different environment in Idaho during the Pliocene. So at this Hagerman fossil beds in Idaho, there are these fossils of these horses and fossils of otters and wetland plants that depict that Idaho was much warmer and wetter than it was today. So this is a really interesting aspect in our national park system that can tell us about the climate that we may be heading towards due to our current 400 parts per million of carbon dioxide. So overall, with the Pliocene epoch, I want you to remember that the last time CO2 was 400 parts per million was during the Pliocene. Okay, so I'm going to take the break of our lecture here, and the next part of our lecture is going to be the Quaternary and beyond.